Hello everyone. In this second part of continuity, we're going to work some examples. So first, we're going to go from the graphical point of view. In this first problem, we want to use this graphic to determine the points at which the function f of x is going to have discontinuity. Clearly, as you can see, we have discontinuity at anything that is a hole or anything that is a break. So for example, here minus 4, we clearly have a hole. So x equals minus 4 is one of those. In x equals minus 2, we have an asymptote, so there's a discontinuity in there. And then later we keep moving. This part is continuous. This seems to be continuous. And there's a discontinuity here. There's a hole, and clearly the function is defined over here. So this break is going to be another discontinuity. X equals 3. And finally, in x equals 5, we can see that there's a discontinuity because the definition of the function is different from the limit. Okay. Now let's take a look to another example. In here, we have a different function, and then we want to state all the values for which f is not continuous at some point x equals a. So essentially the same idea that we just discussed. So clearly in any point where we have a jump, there's not going to be continuity in there. So x equals minus 2 provides a problem. In x equals minus 1, there's an issue as well because there's a hole in here and the definition of the function is in a different point. And also, although it looks weird over here, we don't have evidence of any holes, and the next discontinuity is going to be at x equals 3. Now, we want to know at what points the limit when x goes to a does not exist. Notice that minus 2 is a good candidate, since the limit by the left side is different from the limit on the right side. Now, that's the only point that's going to have that behavior, because over here, in this point, in minus 1, although it's a discontinuity, the limit by the right side and by the left side is going towards the same point. Similarly here. So that's not going to suffer from the existence of the limit. Now, in what point f of a is not defined? Now, from what we can see, f of a is not defined in x equals 3. Is the only point that doesn't have any definition. This has a definition, this has a definition. Now, D, at which values of a does f has a limit, but the limit is different from f of a? So in this case, we can count that as x being equals minus 1, since clearly the limit exists in there, but it's different from the definition. Also, we can kind of talk about that with x equals 3, because the limit exists in there, but f of a does not exist. Okay, so this is some graphical examples of continuity. Now let's take a look to some questions with continuity where we're using a function instead. So in problem 3, we're going to determine where the following functions are continuous at the given value of a. So in the first one, we had the function f of x equals 3x minus 2 over x squared minus 5x plus 6. The first thing that is easy to verify is if the function exists at the point. If it doesn't, then immediately we're going to have a discontinuity. So let's check what the value of f of 2 is. So in the top, we're not going to have an issue. This is 3 times 2 minus 2. And here is going to be 4 minus 5 by 2 plus 6. So this is going to be over here 6 minus 2, and on the bottom is going to be 4 minus 10 plus 6. So as we can see, this is clearly something that is 4 over something that's going to 0, or plugging in this will give me something that is 0. So that means that f of 0 does not exist. So because f of 0 does not exist, f of x is not continuous at 0. F not continuous at x equals 0. Okay, so that's the first scenario that can occur. If we don't have that the function is defined, then it's not continuous. Now let's go for number 2. F of x is x squared minus 25 over x minus 5, and we're wondering if it is continuous at a equals 5, x equals 5. So initially you see that f of 5 is actually defined. F of 5 is defined as 1. Okay, so we have that part. So the second that we have to check is what is the limit when x goes to 5 of f of x. Does that exist at all? Well, let's take a look. If we compute that, we're going to have x squared minus 25 over x minus 5. In this scenario, we have a difference of squares, so we can actually factor this out as x plus 5, x minus 5. And so having that, we get to cancel this, and we're going to have the limit when x goes to 5 of x plus 5, which is going to produce 10. So notice that the limit does exist, but now the problem is that it's not equal to the definition. So the limit when x goes to 5 of f of x is different from f of 5. Okay, so it's not continuous. This breaks the third rule, which is that the limit has to be equals to the definition of the function. Okay, let's move on to another exercise. Okay, we have this function f of x equals x squared plus x over x plus 1 when x is less than 1. 2x plus 1 when x is bigger than minus 1, and we want to check what's going on with a equals minus 1. Is it continuous in there? Is it not continuous? Okay, because this part is including the minus 1, then when I do f of minus 1, I'm going to use this function. So this is going to be 2 times minus 1 plus 1, and this is going to be minus 2 plus 1, so minus 1. So it actually is defined. The function is defined. Now, do we have the limit? That's the second thing. Notice that because we have two different behaviors, we have the function. We have that the function is split into different behaviors. This by the left side, and this function by the right side. So if I take the limit when x goes to minus 1 by the right side, I'm going to have to consider the function 2x plus 1. And so in this case, it's going to be very similar to what we had before, and I'm just going to plug in here minus 1, and I'm going to get minus 1. On the other hand, when I do limit when x goes to minus 1 by the left side, I'm going to have that is going to behave like the other function. So x squared plus x divided by x plus 1. Notice that I can actually factor an x from there. So this is x plus 1 over x plus 1, and I get to cancel the x plus 1 in there. So that becomes limit when x goes to minus 1 of x, which is going to be minus 1. So surprisingly, these two things are equal. And so what's going to happen is that, yeah, the function, it is the same thing as the limit. So we have that these two things not only exist, but they're equal, so this function is continuous at x equals minus 1, or a equals minus 1. So this is one case where we actually had the continuity, and we prove it by showing the function, the existence of the function at the point, and then later showing that the limit exists and there's actually the same to the definition. Finally, if we use the conditions from continuity, sometimes certain functions can be made continuous. So for example, in the following problems, we're going to find constants so we can make the function continuous. So on the first one, we have that f of x is kx if k is less than 2, and phi x squared if x is bigger than 2. Bigger or equal than 2. So notice that the issue obviously is going to be on this point, in the point where they're joining. So what is f of 2? F of 2 gotta be 5, 2 square. So it's gonna be by 5 by 4 is gonna be 20. Okay, so we do have that, and now we want that the limits are the same thing. So the limit on when x goes to 2 by the right side is actually using this same function, phi x squared, and so this is gonna produce a 20. But now we want that the limit by the left side is the same thing. So this is kx, right? But kx, that's gonna be 2k, so that means that 2k should be equals 20. So that implies that if we make k equals 10, then this side is going to be 20, this side is going to be 20, the limit is going to exist, and it's going to be equals to this. So, and this scenario is very easy. We find very quickly the value of k, and we get our continuity very easily. Part 2 is a little bit more difficult, because in here we not only have one constant but 2, and we have 2 different points where we might have discontinuity. We might have discontinuity here in -1, we might have discontinuity in 3. So first, notice that f of -1 is defined as 1, and on the other side f of 3 is also defined as 7. So we clearly have the function well defined. We just need to know the limit. Clearly 1 is the limit when we're going by the left side of the function of f of x. So now what we need is that the limit by the right side when we're going to -1 with the function ax minus b is also 1. So that's going to give me something. This is going to give me an equation. Notice that this is essentially minus a minus b should be equals to 1. So we can get this limit to be equals to that limit. On the other hand, that's going to give us an equation. But on the other hand, I'm going to use the same conditions in 3. So now the limit on the left side when we're going to 3, when the right side when we're going to 3 are going to be 3. I'm going to be 7. That's what the function is defined to be in there. But then we need that the limit by the left side is exactly the same thing. And the limit in the left side is going to be given by ax minus b. So that means that if I plug in 3, I'm going to have 3a minus b is equals to 7. So notice this is giving me an equation. And now from here, I have another equation. I have a plus b equals -1 if I factor this minus. So now I have a system of equations that I need to solve to find that values of a and b. I have 3a minus b equals 7. And I have a plus b equals -1. I can actually find out easily b. I can say from here, well, b is just going to be 3a minus 7. And then I can plug that on the second equation. This is equation 1. This is equation 2. I can plug that in 2. And that's going to produce a plus 3a minus 7 equals -1. So at this point, I'm going to obtain that 4a is equals to, as this 7 is going to move to the other side to add this, so 6. And so that implies that a is 6 over 4, or 3/2. And because we do have the value of A, now we can find the value of B, and B is going to be 3/3 minus 7, and so this is going to be 9/2 minus, and I multiply this by 2 up and down, so it's going to be 14/2, and it's going to be minus 5 over 2. So with these two values of A and B that I just found by system of equation, that's going to make this function continuous now. Okay, and so this is all the type of exercise that we can do when we're dealing with continuity.